So what we have seen so far is that if an implant has angled compression screw slots, while we compress, we will indeed rotate the implant, which will also force the proximal fragment to rotate. And we have demonstrated using cardboard, which was a model with angled screw slots, that in our cardboard the trajectory of rotation at close to the osteotomy site will be this one here. So the movement would be more or less that direction, and we want to investigate whether compression will also be in that direction. Now, to recap, what, for example, the BioCurve plate is advertised to achieve is that after you've placed these two screws without tightening them, while you tighten this screw here, this would create compression this way. And what the company suggests is that this will close any remaining gap at the osteotomy site cranially. And then what the company says, if you use that screw to create compression, then the implant will move that way, which is demonstrated here, creating compression along this path. But what we have demonstrated is that this cannot happen. What we demonstrated that however you grab the cardboard, and no matter what kind of force you apply, the cardboard can only move along one path, and it won't be a path broken into two pieces. It can be first cranially and then distally. However you pull it, it will move along this single path. And we said that the path close to the screws will be here, but the path close to the osteotomy will be here. So what we have shown is that what the company advertises here is not exactly accurate, and they may be doing it to oversimplify something that may not be easy for vets to understand. I can't explain it otherwise. Now, if we go back to the ARC plate from Synthes, what the company has said is that, as we saw it before, the plate will move that direction while you're applying compression with this screw here. So how the arc plate works is that you place this screw here, and that's the pivot screw. You don't tighten that, you don't compression with that, but because this slot is at an angle with that slot, exactly as we demonstrated with our model, when you apply compression with that screw, this screw will pull the plate that way, and this will act as a pivot, and the plate will rotate that way while at the same time is translating distally. And that makes sense. And the company has said that they're doing that because they want their compression vector, which is this one here, to not be parallel to the long axis of the plate. They want it to be angled so that compression on the osteotomy side happens at an angle to the tibial axis. And that's all good. But how do we know how compression happens? All right, so let's look at this example here. This is an example from a university book, and it's called Engineering Mechanics: The Volume of Statics. Now, this example, what they're asking here is that there is a lever, and that's the lever here, and we call it A, B, C, and we're applying a force B to the lever, and the lever will tend to move around this pivot point and will tend to move like that, right, in a circle. But because it's connected to a pin here, the pin will apply a force and will stop the lever from moving. Now, that is the intuitive approach. The intuitive approach is to say that this is the trajectory of the potential movement, and the movement is always tangent to the circle, and hence the pin should apply a force tangent to the circle. And I have drawn that here. Again, this is the circle, and this here is tangent to the circle. So the force must be that direction, but actually, as you see here, the answer is that the pin will be applying this kind of force. So this force here is at a very different angle as the one our intuition have told us to think about. So how did they come up with that a different angle? All right, well, there is a rule. And we use this rule in engineering to solve problems like that, and it makes it very, very, very easy. The rule says that if there is an object, which we call a member, and there are three forces only applied to this member, and this member doesn't move, it's in static equilibrium like this lever, so we're trying to move it. We may move it a little bit, but then it stops moving, all right, because all these three forces cancel themselves out. So if these three forces cancel themselves out, then the lines of the forces must go through one point. So what that means here, so we have this force here, which is the force we apply, and we know the direction of that force. The pivot point also, the pin will apply a reaction force to the lever like so. Now, how do we know the direction of this force? Well, to make the long story short, if you see here, this is the pivot point, and it's connected with a bracket to this point here, and this bracket also doesn't move because the whole system is in equilibrium. You may pull it, but it doesn't move. So this bracket also is in equilibrium, and which means that the force that goes through the bracket will be through these 2 points, which means that the force of that pivot point will be that direction. But anyway, that doesn't matter here. What matters is that we know the direction of the forces, and because we know the direction of two of the forces, and we know that all three forces will go through the same point, then we can find the point that these two forces will go through. And if you draw the line of these two forces, we find out that they go through this point O. So it must be that the third force will go through point A, because this is the point of application of the force, and the line will go through point O. So this must be the direction of this force. Now, they also calculate the magnitude of the force, which we don't really care about right now. What we care about is what is the direction of the force that will stop an object from trying to move in a circular trajectory. And what we found is that if the tangent of the trajectory is that, which means the direction of the potential movement is that, the force that will stop it from moving is very, very different than the um, direction of the tangent. Does that make sense? Well, intuitively it may not make sense, but I will give you a very, very oversimplified and short example to make sense of it. So this is the example. Let's say that we have this trajectory, it's a circle, and there is an object here, and we are here in the middle of the circle, and we are tied with a tie. We're taught with a tie to this object, and we do that, and we allow the object to move in a circular motion. And what I mean by doing that is that we apply a centrifuge force, don't we? We have to apply a force like that so that the object keeps moving in a circle. If we don't apply this force, the object will go straight through, will follow a linear path. So we need to apply the centrifuge to keep changing its velocity, actually to keep changing the direction of the velocity. And that's what we call angular acceleration. But that doesn't matter. What matters is we understand what we're doing here. We're applying a force that direction, the centrifuge, but our object moves in a circular trajectory, and we know that in each instant in time, in each point in time, the direction of the movement, which is the direction of the velocity, will be in on the tangent of the trajectory. Now the question here is, how would you stop this object from moving? What kind of force would you apply? Now, intuitively, before we said we would apply a force that is opposite to the direction of the movement. All right, if you do that, that's fine. It may stop moving like it's moving now, but remember, there is a centrifuge force. So it will not completely stop moving. This force that is opposite to the direction of the movement will not stop the object because there is also a centrifuge force. So how would we stop this object? All right, well, let's say what I would do, first, I would apply a force exactly opposite to the centrifuge force, because this force would eliminate the centrifuge. So these two forces would cancel themselves out. And then what would happen is the object will start moving on a straight line because there is nothing trying to change the direction of its movement anymore. So it will go on a straight line. Now I would be able to apply a force opposite to the direction of the movement to stop it from moving. What does that mean? I would apply one force here, let's say F1, and another force here in order to stop it from moving. So if I wanted to apply only one force, then that force would be the force that could replace these two forces. And the force that can replace two forces is the sum of these forces. And if you remember from high school, all we have to do is with the parallelogram law, draw this force here. So this would be the force F that would stop this object from moving. And that's very similar to what we found previously, wasn't it? We have found that to stop this point here from moving that way, well, let me open that way, we need to apply a force that way, right? So that's very similar. Now, what does that have to do with compression? All right, let's look at this. Let's say that we have a column and we apply a force like so in the column, and the surface of the column starts moving like there, and it ends up here. And now the column applies a force like so to us, to our finger, and we can't keep moving it anymore. We can't keep compressing it. Well, we keep compressing it, but we're static now. We can't move anymore. So this is static equilibrium. That means that we apply a force to the object, but the object applies a force back to us, which is equal in magnitude in opposite direction. And because we're not strong enough, we cannot go anymore. So everything is in equilibrium, everything has stopped moving, everything is compressed also. What's compressed? Well, our finger is compressed and the object is compressed. What compresses our finger is the reaction force, which is represented by the blue vector from the object. What compresses the object is the is the force represented by the white vector, which is the force we apply to the object. What's compression? Well, compression is one of these forces, right? If we know one force, we know the other because they're equal magnitude and opposite in direction. So if you say what's the compressive force here, the answer could be, well, I'm compressing the object with a force white. And or you can say the object compresses me with a force blue. It doesn't really matter. All right, so going back to this simple example, let's say that we allow the object to keep moving there like that, and that's the object. And now we want to place a surface here so that the object hits on the surface and stops moving. All right, stops moving. So if that happens, if we manage to find a way to put the surface in such a way that the object stops moving, What does that mean? That means that the surface has applied a force like so to our object. We know that because we know what direction the force must be to stop this object from moving. All right. But if our surface has applied a force like that to the object, and the object after 2, 3, 4, 5, 6 minutes stops moving, um, it means that also the object has applied a force like that to our surface. All right. So it must be, because if there was a different force applied by the object to the surface, then the object would not have stopped moving. So that means that if we know what force we need to apply to an object to stop it from moving, then we know the compression that happens within this area, the contact surface area. All right, so now let's go back to our actual problems, and let's start with the BioCurve plate. Well, first of all, we figured out that the plate doesn't move exactly as described. It doesn't move cranially and then distally. There is only one trajectory that it follows. Now, what we want to know is, does it actually compress cranially or distally or something in between? Let's figure it out. So what do the guidelines say here? The guidelines say that first we apply here this screw. All right, we place this screw in. Then we place this screw and this screw, so some couple of locking screws to anchor the proximal fragment to the plate. And then we apply compression with this screw here. What does that do? Well, let's see. Let's go here. So if this screw is in place and we apply compression with that, what will that happen? Well, the screw moves along the axis of the slot, doesn't it? Let's say that this is the axis of the slot. So it means that it should be pulling or pushing the plate that way with a force like that. Now, as the plate moves that way, the screw comes in contact with the plate here, this surface here, which means that if it comes in contact with it, it must apply a reactive force to the plate, because the plate wants to move that way, but the screw is there and the screw pushes it on the opposite direction. Now, how do we know? Right, we know the direction of this force here, but how do we know the direction of the reaction force from the pivot screw? All right, you may remember from high school that if we have a surface, no matter what kind of force we apply on it, if the surface is smooth, which means frictionless, then the surface can only apply back to us a force that is perpendicular to it. All right, and that's why when I apply a force like that to my phone, my finger slips down, because the phone surface cannot apply a force like that opposite to my force. It can only apply a force like that. So my force will slip down. So what that means here, we have a slippery surface, which we call a smooth surface, and the force will be perpendicular to the smooth surface. And you may say, well, yes, but it's not a flat surface, it's a curved surface. Fine. So we'll find the tangent of this curved surface, and the force will be perpendicular to the tangent. So this is the force. Now let's see. We have this line. This is the line of this force, and this is the line of this force. Well, let's make it that it meets there. So, and they meet here. All right. Is there a third force? Well, it must be a third force, because as the plate keeps rotating and moving down and whatever, let's say that this is the trajectory of movement of the plate, it means that because it's anchored to this proximal fragment, it moves this fragment in the same trajectory, and as this fragment meets the distal fragment will apply a reactive force, so that it stops the proximal fragment from coming on it. Exactly the same example as we said here, when we said that our finger will applying a force to the column, and the column will start applying a force to our finger until we can't apply any more force because the force from the column is high enough that we can't overcome it, so the movement will stop. So exactly the same will happen here. The reaction force from the distal fragment will not be able to be overcome by the force of the proximal fragment, so movement will stop, and the column, the member, will be in equilibrium. And what's the member here? What's the object that's moving? It's the plate with the proximal fragment. That's the member that's moving. And the member will come in equilibrium, which means that all the forces acting on the member must go through the same point here. And what are the forces going through the member? We said one force is the force this screw applies on the plate. The other force is the reaction force from the pivot screw that is applied on the plate. And then we have also the reaction from the distal fragment that is applied not on the plate, on the proximal fragment, which is anchored on the plate. So this reaction force must follow the direction of a line like that. All right, you may say, how do I know that the line is not there or is not there? Well, it may be, but it doesn't matter for the purposes of this video here. It will be more or less like that. And what matters really here is that compression will happen in that direction. All right, because the distal fragment will apply a force like so to the proximal fragment, and the proximal fragment will apply a force like so to the distal fragment. So this will be, compression vector will be on this line, this direction. Is that important? I think it is important to know how we're compressing. We're compressing like that, but the plate is not moving cranially to close the gap. The plate is moving following a certain path. Now, what's next? After we've done that, guidelines say we need to tighten this screw now. All right? All right, so let's say everything has stopped moving, and let's take this and get it out of the way. Right, now we have placed the screw, we've placed all screws, and now we start compressing with that. So as we tighten this screw will pull the plate that direction. Now, as the plate is moving that direction, it will come in contact with this screw here, and the screw will apply a direction like that, a force in that direction, sorry. Now, if we draw the lines of these forces, they will meet here, which means that the third force will be something, sorry about that, will be something, let's say, like that. So compression now will be happening here. So what's the point of first applying compression like so, and then ending up applying compression like so, if our plate is not moving cranially anyway, and if our plate is going to move only towards one direction, is going to follow only one trajectory anyway? There may be a reason why. And the reason may be because when you, after you have tightened this distal screw, the plate has moved along a bit along this path. Let's say that it's moved a little bit like that. And then after you apply the proximal screw, it moves a little bit more along this path. So overall, it's creating more compression at the surface. And that may be a good thing. Otherwise, you would end up with less compression if you only had used, for example, this screw to compress. So if you want to use two screws to compress, then the company's guidelines that you first need to compress with that and then to compress with that seem quite rational. What doesn't seem rational is that you will be ending up with two kinds of compressions. It's not the point. You will be ending up with only one compression, and there won't be any closing of the cranial gap. There may be some, but not because the plate moves cranially and then distally. Now, if we move on very quickly to the arc plate, things are quite similar here. The company says that we should apply this screw first, which is the pivot screw, and then we need to use this screw to compress. And as we push the plate distally by tightening this screw, then this plate, this screw here, will come in contact with the surface of the hole, and it will apply a force, a reaction force to the plate like so. And where are these going to move? They're going to move, they're going to meet, sorry, where are they going to meet? They're going to meet here, more or less, which means that the compression will be somewhere either here or here. We don't really know here, well, as we didn't know before, but compression could be there, could be there, could be there. The company says it would be there, maybe, more or less, who knows. Now, I have to say, I have asked the company whether compression would be uh, towards that direction, as they show on their explanatory video, and they have come back to say that they haven't tested that, but it is definitely sure that compression is not happening on the long axis of the bone. It is a little bit oblique on that, and that was the company's objective. Now, what is interesting to note is that if this hole here was a little bit angled, more like that, like the BioCurves plate, then exactly as the BioCurves plate, this force would be like so, and this force would be like so, and these forces would meet up somewhere here, so compression would be in a much more oblique angle, if that's what we prefer. So I don't know why Synthes chose to only redirect the direction of compression that little. Uh, but they must have the reasons. Uh, in any way, this is not a review about the implants, it's a review about the mechanics of the implants. Both implants, as I said in my first videos, are great implants. I've used them both, not a lot of times, but I've used them both and I was impressed by both. I hope that these videos shed some light to the inquiring mind. And if you have been troubling yourself with questions like that, how does compression happen in these cases, then I'm hoping that you are more close to the truth now than you were before these videos. Thank you very much for following.